When looking at a modern computer architecture, the division between CPU cache and main memory looks like a standard software abstraction. But since 1975, virtually all computers have relied on this bifurcated memory system because no single physical memory type can do everything. This table breaks down the two dominant memory types, SRAM and DRAM. Looking at the top rows, both are volatile, losing data without power, but their operational profiles differ completely. SRAM is extremely fast and expensive, while DRAM offers moderate speed at moderate cost. The CPU requires both of these profiles to function. It needs the extreme speed of SRAM for its immediate cache and the economical density of DRAM for bulk storage. This macroscopic system architecture is entirely dictated by microscopic constraints at the single transistor level. To write truly optimized system-level software, an engineer must understand the absolute physical trade-offs forced by these two distinct circuit designs. Before diving into the physical circuits, we need to establish how the CPU interacts with memory conceptually. Despite the physical differences between cache and main memory, the CPU interfaces with them using a strictly uniform abstraction layer. This block diagram illustrates the communication flow of a typical memory unit. To communicate with a specific memory byte, its location number is transferred to the Memory Address Register, or AMR. An internal address decoder takes this location from the AMR and opens the specific physical pathways needed to access the requested byte. The information then transfers in and out of the memory unit through one common gateway known as the Memory Buffer Register, or MBR. Moving past the AMR and MBR interface registers, we can examine the internal organization of the memory unit itself. This diagram represents the memory unit as a conceptual two-dimensional array of bit cells, where each cell stores exactly one bit. The physical array has two metrics. Depth represents the number of words, and width represents the size of the word in bits. If an address register has n bits, it can specify up to 2 to the power of n memory rows within that array. The MAR and MBR successfully abstract the underlying hardware into a simple 2D grid, hiding the severe physical compromises happening inside the memory chips. To understand those physical compromises, we look first at the actual physical construction of static RAM, or SRAM, the hardware used for CPU cache. SRAM is constructed using the exact same process technology as the CPU logic itself. This schematic shows the defining physical characteristic of SRAM, the 6-transistor, or 6T, memory cell design. The core mechanism relies on 4 transistors, T1, T2, T3, and T4, that are cross-connected to produce a highly stable logic state. When a logic state of 1 is held, point C1 remains high and C2 remains low. This configuration keeps specific transistors locked perfectly on or off. Because of this stability, SRAM requires no refresh cycles. It holds data perfectly for seconds, minutes, or days, as long as direct current power is applied. The address line at the bottom of the diagram controls the 2 remaining transistors, T5 and T6. Activating the address line opens T5 and T6, allowing the system to instantly read or write via the external bit lines. This physical design directly determines system performance. SRAM utilizes single-level decoding, meaning it dedicates one physical pin for every single address line. This direct addressing allows for incredibly fast access times, often measured in fractions of a nanosecond. But requiring 6 transistors per single bit makes the SRAM footprint physically massive, rendering it much less dense and vastly more expensive than the alternatives. While the 6T architecture provides the extreme speed required by a CPU core, its sheer physical size makes it impossible to scale up for gigabytes of main memory. To achieve the bulk capacity needed for main memory, the hardware industry uses dynamic RAM, or DRAM. DRAM drastically reduces the cell size. It replaces the 6 transistors with just 1 transistor and 1 tiny capacitor. In this simplified circuit, the capacitor holds an electrical charge to represent data, and the transistor acts as the access switch. This design has a severe physical compromise. The tiny capacitors constantly leak their electrical charge, meaning the stored data quickly evaporates. To prevent data loss, an external memory management unit, or MMU, must constantly read and rewrite or refresh the data, which consumes processing time and power. This extreme density creates a massive secondary engineering hurdle, the physical pin count problem. If a modern 4 GB memory stick used SRAM's single-level decoding, it would require an impossible 4 billion AND gates and physical routing lines. This schematic outlines the architectural solution to this bottleneck: address multiplexing via 2-level address decoding. Instead of dedicated lines, the multiplexing system reuses the exact same physical address pins for 2 different tasks sequentially. This system first sends the row address and locks it in. Then it sends the column address over those exact same lines to pinpoint the specific bit. This method successfully cuts the required physical pins in half, but it inherently slows down memory access time by a factor of 2. DRAM achieves the extreme density required for main memory, but its volatility and multiplexed routing make it far too slow to feed a modern processor directly. Combining these 2 different hardware paradigms explains the modern computing landscape. SRAM's fast, single-level design earns it placement directly onto the processor chip as cache. DRAM's dense, multiplexed one-transistor design banishes it to the motherboard as vast external main memory. During execution, the system must constantly predict and pull bulk data from the slow DRAM, staging it in the fast SRAM cache for the CPU to process. This complex hierarchy is not an arbitrary choice by OS developers. It is a strict physical imperative dictated by transistor physics. High-performance code must be written to respect these hardware boundaries to avoid stalling the CPU. True system programming is the art of writing software abstractions that perfectly align with the microscopic physical laws of circuit hardware.